Alrighty, good morning, lads and ladies. Welcome back. Today, we are going to kind of conclude the story on power series. We're going to get the big result that everybody wants, and that is a very general formula for how to get the power series for any function. Such a powerful formula is necessarily going to be a little bit complicated, which is why we introduced the notation we did at the end of class last Friday. So let's go ahead and do that. I know you're all anxious about the exams. I did get a couple done over the weekend, but not as many as I was hoping, if I'm honest, because we had a bunch of stuff going on. But I will continue grinding on those tests, and we will get the results together here. Let's go. All right. You guys need the screen share. Okay, so this is MAC 2312, section number 004, which is a Calc 2 class, and date today. What is today's date? 28. All right, so today we're going to talk about sections 11.10 and 11.11, which are both on Taylor's theorem. The textbook actually goes into, this is one of the few places where the textbook goes more granular and more detailed than I feel like we need. Specifically here, there is a discussion of what's known as the error term, or kind of inequality relating the accuracy or speed of convergence of a Taylor series. We're not going to cover that. So the section there that you see, if you read the textbook on Taylor's inequality, is not something that I'm going to test you on. As promised, there's only one estimation theorem that I require you to learn in this section of the course, and that is the estimation theorem for alternating series, because it is actually the case that the Taylor inequality is very, very similar, almost identical in every case where we would use it in this class to the estimation theorem for alternating series. So with that said, we are going to cover these two sections today, and the place to begin is with a definition, or I should say a theorem which kind of has a definition in it. So this is Taylor's theorem. I'm not actually sure the man Taylor that this is named after. I'm kind of curious now because I had someone ask me earlier. Brooke Taylor? Yeah, named after Brooke Taylor. It was not someone I am familiar with, if I'm honest. That's kind of shameful. But, yeah, okay. So Taylor's theorem says the following. If f is a function having derivatives of every order at x equals a, and this would mean that like f of a, f primed of a, f double primed of a, and so on, all exist, right? So f is infinitely differentiable. That's what we're saying here. If f is infinitely differentiable at a, meaning f of a, f primed of a, f double primed, f triple primed, all the derivatives that you could possibly want to take at a exist, then f can be written as a power series. In analysis, we call this being analytic, right? Being expressible as a power series, which is almost exactly the same thing as being infinitely differentiable, right? This is like being infinitely differentiable at A. Means you are analytic at A, which means you can have a power series centered at A. So that means f of x can be expressed as a power series sigma n from 0 to infinity cn times x minus a to the n. And Taylor also provides us a formula for the coefficients, where cn is the, remember what this notation means, this is the nth derivative, think of this as like n primes up here, the nth derivative of f evaluated at a, and this is the slightly weird part, divided by n factorial. This theorem is a huge deal, right? With your favorite like Donald Trump bizarre, pronunciation of the word huge. However you want to emphasize it, this is probably the most important single mathematical theorem in all of like engineering dumb and all of like computer science dumb and all of probably in differential equations land here in mathematics, certainly in physics, maybe the single most important analytic result in the last 500 years or something. It does two things. It guarantees the existence of a power series. That's nice, right? Saying f can be written as a power series. And it also gives us a recipe to get the power series for like any function, as long as that function is infinitely differentiable. So there are some functions that we would like to have a power series for, but we do not yet have a power series for. And I'm thinking the calculus functions that are super important to us, like e to the x, sine x, cos x. So far, we have power series for like 1 over 1 minus x, inverse tangent of x, natural log of 1 plus x. Those are all very nice. But the trig functions, we don't yet have a power series for, and the exponential, we don't yet have a power series for. So we really want those things. And this formula is going to give us the ability to get that. I think the best way to start wrapping your head around this thing is to practice with it. So let's go ahead and use this. I'll show you two examples where we do a raw calculation just using this formula, this theorem. Questions on what the theorem is saying, the notation, before I do that? All right, then let's take a stab at it. So let's use Taylor's theorem to find a power series for the function e to the x. And we're going to center the series at 0. A little note. Power series centered at a equals 0 are called, you can call it a Taylor series, right? That is fair. People do that. Sometimes they call these Maclaurin series. I guess Taylor and Maclaurin were two mathematicians of the era, and probably Maclaurin discovered the version of this formula where a is equal to 0 before Taylor found the general one for just an arbitrary center, a. So sometimes your homework or web assigned the textbook will refer to a power series centered at 0 as a Taylor series, but it means the same thing. Doesn't mean anything special. the way I recommend you do this is by making a little table. So the thing that we need are the coefficients Cn. Once we find a formula for these things, we can just plug them in here and bam, you got your power series. Of course, this formula is somewhat complicated. It's the nth derivative of f evaluated at the center, all divided by n factorial. So I like to build it up. The example we're going to do right now is extremely simple, but you'll see that these can get quite hairy. McLaurin, M-A-C, like the car, M-A-C-L-A-U-R-I-N, McLaurin. McLaurin series. So the way we're going to use this table to come up with the power series is by filling out one row at a time and figuring out sort of what C0 is, figuring out what C1 is, figuring out what C2 is, and eventually finding a pattern and taking a guess at what Cn is in general. So I like to start by filling out the n equals 0 row. This column is just n. This is the nth derivative of your function as a function. This is the nth derivative of your function with the center plugged in. In this case, a is 0, so we'll be plugging in 0. And this is the nth Taylor coefficient. It's what you get by dividing the previous column by n factorial, according to this rule. So if I differentiate e to the x 0 times, it's going to stay e to the x. If I plug in 0, my center, for x, I get e to the 0, which is 1, which means that C0 is 1 divided by 0 factorial. And remember, 0 factorial is just 1. That's one row of the table. What we're going to do is fill out several rows and then look for a pattern. So the n equals 1 term is going to come from the first derivative of e to the x, which is just e to the x. And if I plug in my center, that's e to the 0, which is 1. And then to get C1, you just divide this by 1 factorial. So C1 is 1 over 1 factorial. If I differentiate my function twice, if I look at the n equals 2 row, the second derivative of e to the x is still just e to the x. If I plug in the center, I get e to the 0, which is still 1, which means that C2 is going to be 1 over 2 factorial. What you notice is that no matter how many times you differentiate e to the x, it's always going to stay e to the x. So this guy is nice and simple. If I were to do this n times, the nth derivative of e to the x is still e to the x. And if you plug 0 in, you're still going to get 1, which means that Cn must be 1 over n factorial. That's it. This is all the work. You can imagine how if your function is something more complicated, right, taking derivative after derivative after derivative here can get quite messy. So in general, coming up with this bottom row is not easy. But for this function, it is, because e to the x is always e to the x when you differentiate it. So now I take this and I plug it in here. So f of x, according to Taylor's theorem, is sigma n from 0 to infinity Cn times x minus a to the n. Here a is 0. So that means we get sigma n from 0 to infinity, 1 over n factorial times x to the n. X minus 0 is just x. That's it. F of x was e to the x. So what we have here, the Taylor series or Maclaurin series, whatever you want to call it, it's a power series for e to the x. And that's a big deal. The IOC for this series is negative infinity to infinity. And we've actually done that calculation as an exercise in the past. For what values of x does this particular power series converge? We just didn't tell you back then that it was the power series for e to the x. So this guy goes on your list of important power series to remember forever and ever and ever on them. I'm going to restate that list for you and show you where it is in the book by the end of class today, because I want to make sure everybody has it in a nice place. But this is the gentlest possible example using Taylor's theorem to find a power series. Are there any questions on what we did here? Where any of those entries in the table came from, or how we were able to use that to find the series expression? Okay. Moving on then. Oh, I see. Yeah, that's a bit of a challenge. Well, maybe what I can do. Let's do one more example, and then I will kind of sketch up a proof for you. We'll try some slightly different feeling problems to give you a bit of context. Let me pull up. So the classic next one to do is sine, but sine is actually a little bit tricky. So before we jump to the power series for sine, let me see if I can find another example that's. Yes, we'll go through the proof later. The x is sine. We're not going to do that. We're going to do something else. One on zero terms, find the Maclaurin series. 2 to the x, x plus x. Let's do this guy. Let's find the Maclaurin series. Remember, Maclaurin series is just a power series centered at 0 for 2 to the x. This is a pretty good one. So I'm going to build that table, and the nth derivative of f, the nth derivative evaluated at the center, and the coefficient Cn. We're going to do the same thing. So I'm going to fill out this table one row at a time, starting with n equals 0. If I differentiate 2 to the x 0 times, then that stays 2 to the x. If I plug in the center, which here is 0, I get 2 to the 0, which is 1, which means that C0 is 1 over 0 factorial. Who remembers the derivative of 2 to the x? What goes here? What is the first derivative of 2 to the x? What is f primed? Very good. One correct answer, one almost correct answer. Yeah, the derivative of 2 to the x is 2 to the x times the natural log of 2. In general, so recall, if you differentiate b to the x, you get b to the x times the natural log of b. Right, so the first derivative of my function here is 2 to the x times the natural log of 2. If I evaluate this at 0, I get 2 to the 0 times the natural log of 2, which is just natural log of 2. So C1, to get the entry in the far right column, you just take this guy, whatever you get here, and divide by n factorial. Here n is 1. So this is the natural log of 2 divided by 1 factorial. My advice is do not simplify in this right-hand side. Leave 0 factorial as 0. Leave 1 factorial as 1, because we're going to be looking for patterns in this far right column to get our final answer. If I differentiate again, right, coming down here, I'm going to start my n equals 2 column. That means what goes here is the second derivative of 2 to the x. Well, here's the first derivative, so we just differentiate that again. Remember, natural log of 2 is a constant, so it's really just this piece I'm differentiating. So I get 2 to the x times the natural log of 2 times the natural log of 2. So that's 2 to the x times the natural log of 2 squared. And if I evaluate this at 0, I get 2 to the 0 times the natural log of 2 squared, which is just natural log of 2 squared. So C2 is the natural log of 2 squared divided by 2 factorial. Just plugging into Taylor's theorem, which says that Cn is the nth derivative of f evaluated at a divided by n factorial. I'll do 1 or 2 more here until we see the pattern. Remember, we're looking for a pattern in this column. So the n equals 3 row of my table means I need the third derivative of 2 to the x. It means I need to differentiate this 3 times. Well, here's the first derivative, here's the second derivative. So if I differentiate this again, I'll get the third derivative. That will be 2 to the x times the natural log of 2 cubed. All right, every time I differentiate 2 to the x again, I get another copy of ln2 from this rule. So evaluating this at 0, I get 2 to the 0 times the natural log of 2 cubed. 2 to the 0 is 1, so this is just the natural log of 2 cubed. And then I divide that by 3 factorial to get C3. C3 is the natural log of 2 cubed divided by 3 factorial. Again, we're looking for patterns. What Taylor's theorem says is that if you know all the derivatives of f at a, in this case at 0, that will tell you the power series. Just divide that nth derivative by n factorial, and that's the coefficient. So I'm looking for patterns in these columns. The pattern I see here, 2 to the x, 2 to the x log 2, 2 to the x log 2 squared, 2 to the x log 2 cubed. If I were to differentiate n times, I would get 2 to the x times the natural log of 2 to the n. The 2 to the x always stays, and every time you take a derivative, you just get another copy of ln2. If you evaluate this expression at 0, you get 2 to the 0 times the natural log of 2 to the n, which is just natural log of 2 to the n, which means that Cn must be the natural log of 2 to the n over n factorial. And really, through this whole process, it's this thing that I'm looking for. Once I know the Cn's, I just plug that into the formula. So therefore, by Taylor, this function 2 to the x is sigma n from 0 to infinity Cn times x minus a, which is 0 to the n, is sigma n from 0 to infinity natural log of 2 to the n over n factorial times x to the n. Oh God, yes. So there's a DM here. This can get really messy. Fuck yes, it can. This can be horrifically messy. So like I said, it's a trade-off. The theorem is extremely powerful in that it says, give me any function, I can find you the power series. The trade-off with powerful theorems is that usually there's a lot of work that goes into it. So I'm going to show you 2 more examples here today. 2 more examples where we do just raw calculations like these. This will be something you're tested on. So it is a skill you need to develop. Before I do that, I want to give you a tiny bit of insight into where the fuck this shit's coming from. Questions on this calculation? Yes, anytime with a small caveat. So what Taylor's theorem says is that any function is equal to sigma Cn times x minus a to the n. And what this table does is it finds you Cn. So yeah, you're always going to just multiply by x minus a to the n, where a is your center. It's not necessarily always going to be 0. Here they said Maclaurin series, so that means a is 0. That's the comment from the previous page. Maclaurin series means you're centering at 0. So you'll always take this thing after you find the pattern, multiply by x minus a to the n, whatever a is, and sum from 0 to infinity. Correct. If we were centering this series at 2, then this would be x minus 2 to the n. But if we were centering the series at 2, that would change this column, right? Because you'd be plugging in 2 for x, not 0. So I'll try to do one example where the center is not 0 also. Other questions about this calculation? Okay. So I want to give you a little bit of insight, but I don't want to overwhelm you. So rather than a full proof of Taylor's theorem, let me just say exploring. Taylor's formula. Taylor's formula says f of x is sigma n from 0 to infinity cn times x minus a to the n, where cn is the nth derivative of x, nth derivative of f evaluated at a over n factorial. That's the formula. If I plug in for those cn's, this becomes sigma n from 0 to infinity fn evaluated at a over n factorial times x minus a to the n. And what I'm going to do now is just write out the terms of this series. This is f0 of a over 0 factorial times x minus a to the 0 plus f1 of a over 1 factorial times x minus a to the 1 plus f2 of a over 2 factorial times x minus a squared plus blah, blah, blah. All right, the next one is f3 of a over 3 factorial x minus a cubed, and so on. I want to focus on these first two terms. I'll clean up all three of these, but I want to take just a second to ask about these. Remember this notation, f superscript n of a. That's the nth derivative of f with a plugged in. So what is f0 of a? What is this thing? How many times have I differentiated here if the superscript is 0? None, right? So this is take f, differentiate 0 times, and then plug in the number a. This is f of a. Zero factorial is 1, so f of a divided by 1. Okay, that's still f of a. X minus a all to the 0. Well, that's also 1. So this whole first piece here is just f of a. I know it looks scary in this notation, and we need that notation for the higher order terms. But this first piece, the piece you get here when you plug in 0 for n, is just f of a plus. What is this? F superscript 1 of a. How many times have I differentiated? Once. So f1 is f primed. So this piece is f primed of a. 1 factorial is 1. So this is f primed of a times x minus a to the 1 is just x minus a plus. This is f superscript 2 of a. That means that's the second derivative of f evaluated at a divided by 2 factorial times x minus a squared. So I can write that as f double primed of a over 2 factorial is 2 times x minus a squared. Look at these first two terms. What is this? Think back to Calc 1. If I just said y equals this thing, Newton's law, maybe kind of reminiscent of Newton's method, right, for finding roots a little bit. Think simpler. This is the tangent line. Yeah, linearization, same thing. This is the tangent line, or another word is linearization of or for at x equals a. The first two terms of any power series are the tangent line. Now, when I say first two terms, I mean the constant term plus the linear term. So when I teach linearization or linear approximation, those of you who had Calc 1 with me, remember that the thing they call L of x, the linearization, is the same thing as the tangent line, just solved for y. This is the tangent line, or the line that best approximates f at a. What do you think if I include the first three terms? What do you think that thing is? First, linear function, right? If I just take these first two terms, there's no x's here. This is a constant. There's an x to the 1 here. So this is indeed a line, right? A is a constant, f of a and f prime of a are constants. So this really is just a line, and it is the tangent line, or linearization for f at a. If you go out to the quadratic term here, where you have an x minus a squared, you might call this thing the tangent parabola. It's the unique polynomial of order 2 that has the same first and second derivative as your function. In other words, what Taylor series do, what power series in general do, they extend the concept of a tangent line to tangent parabolas, tangent cubics, tangent quartic, and so on. That's really what's going on here, is you take the same idea as a tangent line, but you apply it to a degree 2 polynomial, a degree 3 polynomial, a degree 4 polynomial. The Taylor series is what you get when you let that run all the way to infinity. So what do I mean by tangent parabola? I mean f primed, and f double prime all match the series. What I mean by tangent cubic is that f double primed, f primed, f double primed, f triple primed all match the series. Remember how I told you to think about power series as just big long polynomials? Well, the Taylor series is the special polynomial such that the derivative of that polynomial is the same as the derivative of your function when you plug in the center. In general, the capital N partial sum of the Taylor series for f of x is, well, it's called Tn of x, and it is, of course, by definition, it's the capital Nth partial sum, so that's the sum from little n equals 0 to capital N of f little n of a over little n factorial times x minus a to the little n is this thing. That is the unique polynomial of degree capital N, which has the same 0th derivative, first derivative, second derivative, third derivative, out to capital Nth derivative, and such that Tn of a is equal to f of a. Tn primed of a is equal to f primed of a. Tn double primed of a is equal to f double primed of a. And you go all the way out to the capital Nth derivative matches. So how did Taylor discover this stuff? What was he thinking about? What Taylor was thinking about was, okay, power series polynomials. How can I pick the coefficients of that polynomial so that the first derivative of my polynomial is the same as the first derivative of my function that I want a series for? How do I pick the coefficients of that polynomial so that the second derivative of my polynomial is the same as the second derivative of the function I'm looking for? And so on. So this is the guiding light for Taylor. He said, I need my series to spit out the same thing as f when you plug in a. I need my series to spit out the same thing as f primed when you plug in a as my series would spit out when you differentiate it and plug in a. I want the original function, the first derivative, the second derivative. I want all of the derivatives to match, but only at this one x value, at the x value a. So my series has the same slope, right? Has the same y value, same slope, same concavity. That's the second derivative. Let me annotate this. So same y value at x equals a. This means same slope at x equals a. This would mean same concavity, or in Calc 3, you'll learn the term curvature at x equals a, and on and on. What Taylor realized is that if you build up a big infinite polynomial that has the same y value at that point, the same slope at that point, the same curvature, concavity at that point, you make all the derivatives match just at that one point, then that polynomial is forced to be the same thing as your function everywhere on the interval of convergence. And this was a huge deal. Brilliant, man. Brilliant deduction. I'd like to demonstrate this for you. We've seen one picture of this before. Let me pause that and take a second to watch this. So don't worry too much about this. This is the capital Nth Taylor polynomial for the cosine function, centered at 0. I'm going to cook this formula up for you a little bit later, but what I want you to do right now, the blue is the Taylor polynomial. The red obviously is cosine. What I'm going to do is first let me turn this off. The center here is 0. So watch what happens as I look at more and more terms of the series, higher and higher degree Taylor polynomials. Here, n is equal to 1. I'm sorry, n is equal to 0. So we're looking at just the constant term, right? It's just this part. And you see that at the center is 0, the blue and the red match. If I increase n by 1, what I'm looking at here is actually the degree 2 Taylor polynomial. So this guy has the same slope at 0. If you look at the blue, the slope is the same. And so is the concavity, right? This is concave down with the right amount of stretchiness, and it goes through that point. Well, watch as I let n play. This is what it looks like for a Taylor series to converge. Pretty cool, right? So these blue things, these are polynomials. And as the polynomials get bigger and bigger, we take more and more terms. I'm forcing the shape to be perfect at this point. And forcing the shape to be perfect at this point makes the blue stick to the red further and further out. I think it's quite lovely. I'm going to show you one more example like this, because this guy only has even ordered terms. Let me turn this off. Look at this one. Same sort of thing is going to happen now. The red function here is e to the x, and you recognize this 1 over n factorial times x to the n. That is the terms for the Taylor series, right? E to the x that we found as our first example. Here, n equals 0. This is the order 0 Taylor polynomial. All it does is match the function at the origin, right? All it does is agree with the function there. If I look at the first order Taylor polynomial, it's the tangent line. Like we said, this is just the tangent line. It goes through the point 0, 1, and it has the same slope as the red function at 0, 1. But it doesn't have the right curvature, right? It doesn't have the right concavity. If I increase n 1 more, now we go through that same point. Now the blue goes through the same point as the red at 0. Has the same slope, right? If you zoom in here, the blue and the red have exactly the same slope at that point. But also the blue has the same curvature. It's concave up and it's stretched just the right amount. This is what I mean by tangent parabola. If I increase one more time, I get the tangent cubic. This has the correct y value, the correct slope, the correct curvature at that point. It also has the same third derivative. And as I increase n more and more, you will see the blue kind of snapping or gluing itself onto the red further and further out. Pretty cool, right? This is what it looks like for a Taylor series to converge to a function. And now the blue and the red are the same. If I pause out here at some large value of n, you can't tell the blue and the red apart. They look like the same function. Now, in order for them to actually be identical, like perfectly the same, you'd have to let n here go all the way out to infinity. Now, of course, we can't do that in the computer, but we can do that on paper. And that's precisely what Taylor's theorem says. Oh. Taylor's inequality, by the way, the part that we kind of skip over, says how far away is the blue going to match up with the red? That's it, right? So you see, even with n equals 50 here, the blue does eventually separate from the red as you get further and further from the center. How far away will the blue stay glued to the red? That's what Taylor's inequality talks about. And you'll get to learn a lot about that if you take a real analysis class. But I don't want to push you guys too hard at this level. What I really want you to do is have that picture in your head and have the ability to do and work with the calculations. So the next thing I want to practice with you is another problem, finding Taylor series. This one's going to be a little bit subtle, not hard. The calculation here is not hard, but it's going to require some critical thinking. So same task, let's find the Maclaurin series for f of x equals sine x. And again, Maclaurin series means centered at 0. I will try to squeeze in a calculation where the center is somewhere else before the end of class. Oh, yes, I see something in chat here. Go back to the last page for a second. Sure, just for 1 second. Here's the end of the last page. Oops. Sorry, I forgot we're split between 2 papers. So here we go. Is this what we needed? While you're writing, I'll just say the magic that forcing the polynomial to have the same nth, like 0th derivative, first derivative, second derivative, third derivative, forcing all the derivatives to match just at that one point somehow makes the function match everywhere is very special. It's not obvious. The last one here, I don't have there's no neat geometric interpretation because capital N is just capital N, but this says same concavity or curvature. Remember, like concave up, concave down from Calc 1, that's determined by the second derivative, right? The more general term for that concavity thing is called curvature. So concavity just says like concave down or concave up. Curvature is like how fat or narrow, how tightly curved the thing is. I have fairly low curvature, and quite rotund, but a very skinny person would have small curvature. I'm sorry, would have large curvature because they curve tightly. All right. So let's return to this. I want to find a Maclaurin series for the sine function, which means I'm finding a power series centered at 0. So I need to calculate the nth derivative. I need to calculate the nth derivative evaluated at my center, which is 0. And from that, I will get Cn, the nth coefficient in my Taylor series. I'm going to give myself a bunch of space here because I know that this takes up quite a bit. We will need to fill out several rows of the table before finding the pattern. Now, that's what I meant when I said this problem is not hard, but a little bit subtle. So if n is 0, if I differentiate sine x 0 times, then I have sine x. If I plug in 0 for x, then I have the sine of 0, which is 0. So C0 is 0 over 0 factorial, which is 0 over 1, which is just 0. Moving on, when n is equal to 1, I'm talking about the first derivative here. So the first derivative of sine x is cosine x. If I plug in my center, that gives me the cosine of 0, which is 1. And then dividing that by 1 factorial, I get C1 is 1 over 1 factorial. And I'll just leave that like that. Coming down one row to n equals 2 now. If I take the second derivative of sine or differentiate cosine, I get negative sine x. Evaluating that at 0, I get negative sine of 0, which is negative 0, which is still 0. So C2 is that divided by 2 factorial. 0 divided by 2 factorial. And 0 divided by anything is 0. Continuing, when n is equal to 3, that means I'm looking at the third derivative of sine, which is the derivative of negative sine x, which is negative cos x. Plugging in 0, negative cos of 0 is negative 1, because cosine of 0 is 1. And that means that C3 is negative 1 divided by 3 factorial. Continuing, when n is equal to 4, I need to differentiate this and give me the fourth derivative of sine. Well, the derivative of cos is negative sine. So this is negative sine x, which is just sine x. We're back around to the start. Evaluating that at 0. Sine of 0 is 0. So C4 is 0 over 4 factorial, which is 0. I'll do 2 more rows here and then try to observe the pattern. When n is equal to 5, the fifth derivative of sine is the same as differentiating this guy is cosine. Plugging in my center, which is 0, cosine of 0 is 1. So C5 is that number, 1 divided by 5 factorial. When n is equal to 6, differentiate again, you get negative sine of x. Plug in 0, you get negative sine of 0, which is negative 0, which is still 0. So C6 is 0 over 6 factorial, which is 0. many of these are 0. From a certain perspective, exactly half of these are 0. The question is, do you see a neat enough pattern over here to write a formula for the CNs? I'd say that this pattern, definitely some things should be jumping out at you, but a nice formula is going to be pretty hard to come by. So tell me, what patterns do you guys see in this column? Anything? Good. When n is even, the coefficient is 0. That's correct. And when n is odd, the coefficient is not only non-zero, but it does follow a nice pattern. 1 over 1 factorial, negative 1 over 3 factorial, positive 1 over 5 factorial. The next one being negative 1 over 7 factorial. So there is a pattern. But it's hard to find a nice formula. From this. So instead, what we're going to do is we're going to just start writing out the series. I'm going to plug these coefficients in to Taylor's formula. And we're going to see, after I simplify and get rid of all the terms which are 0, if there is some nice way to write the resulting series. So we know by Taylor's theorem that sine x, my function, is equal to sigma n from 0 to infinity, Cn times x to the n. The center here is 0. And if I start writing those terms out, that's C0 plus C1x plus C2x squared plus C3x cubed plus C4x to the 4 plus C5x to the 5 plus C6x to the 6, oops, 6, plus C7x to the 7, and so on. A lot of these are 0. So stay with me on this. C0 was 0 plus C1 was 1 over 1 factorial. So I'm going to write that 1 over 1 factorial times x plus C2 was 0. C3 was negative 1 over 3 factorial. So this is minus 1 over 3 factorial times x cubed. C4 was 0. C5 was positive 1 over 5 factorial. So this is plus 1 over 5 factorial times x to the 5. C6 was 0. What would C7 have come out to? following the pattern, what would this guy be? Yeah, excellent. So this would be a 1 over 7 factorial, right? It would actually, C7 would be negative 1 over 7 factorial, right? Plus, minus, plus. So this whole term here would be minus 1 over 7 factorial times x to the 7. And the series would continue on. Now what I'm going to do is I'm just going to stop writing the zeros. Shitload of these terms are 0. I don't need to write them. So I get 1 over 1 factorial times x minus 1 over 3 factorial times x cubed plus 1 over 5 factorial times x to the 5 minus 1 over 7 factorial x to the 7 plus, and so on. So it may be pretty hard to see a formula for the CNs in general, but if you ignore all the even ones and just look at the odd ones, which we can do because the even ones are all 0, if you ignore all the even ones and just look at the odd ones, you get this. And this is not terribly hard to put into sigma notation. So i.e., that is, sine of x can be written. How would you put this into sigma notation? I'm going to start by writing sigma n from 0 to infinity. Think about what we see in that line above. Not quite. It's not quite 1 over n factorial times x to the n, because these are all odd, right? There's no even terms here. So if we just had 1 over n factorial x to the n, that would include a lot of even stuff, right? Every time n is even, we would have a term there as well. But here, just odd terms. All the even terms were 0. Elijah is correct. Yeah. Oh, sorry, it's a DM, so you guys can't see it. So I'm going to put in, that is correct, Elijah. I'm going to put the pieces in here kind of in the order that I think it's easiest to see them. First, positive, negative, positive, negative. This is an alternating series, and the first term is positive, so I can write negative 1 to the n. Next, I have 1 factorial, 3 factorial, 5 factorial, 7 factorial. So what goes down here is the nth odd integer factorial. Well, the nth odd integer, remember way back in section 11.1, that's 2n plus 1. So the downstairs here is 2n plus 1 factorial. And then finally, the power of x, 7 factorial, 5 factorial, 3 factorial. The power of x that goes here is the same as the number that is being factorialed downstairs. So that's x to the 2n plus 1. Here is the Maclaurin series for the sine function. And as you might guess, this is one of those super duper important power series that you need to remember forever and ever. The IOC here, I will do the calculation for you, is negative infinity to infinity. I just want to write it here so it's in your notes together. Real quick, why was it so hard to find a formula for the CNs here, but not hard to find this formula here? Another way of saying it, what's the difference between this and this? Yeah, all the even terms being 0. So let me come back here and do something that not every calc teacher would do at this point, but I feel you guys deserve it. The formula for the CNs here is best described piecewise. We have to think about whether n is even or odd. Which, if n is even, that means n is equal to 2 times k for some integer k. If n is odd, that means n is 2k plus 1 for some integer k. If n is equal to 2k, then Cn is 0, because n is even. If n is equal to 2k plus 1, then Cn is negative 1 to the k over 2k plus 1 factorial. That's actually the formula for the Cn's. And the big difference between this series here and the series we got in our answer down here is that this series has an x to the 2n plus 1. It's only looking at the odd terms. So don't worry about the red formula for the CNs at the top there. If you don't like it, if it feels weird to you, don't stress. It's not a normal part of Calc 2 to require you to come up with this formula. It is a normal part of Calc 2 for you to go through this exercise of writing out the terms, getting rid of the ones that are 0, and then putting this into sigma notation to get your power series for sine. So what I really need you to do is understand how we got this, and then to remember it. I said I was going to verify for you that the IOC is negative infinity to infinity. Let's do that quickly. So I claimed earlier that this should be all real numbers. I just want to make sure that we remember how to find intervals and radii of convergence. The trick, as for pretty much all power series, is to use the ratio test, wherein we calculate L, the limit n goes to infinity, absolute value of an plus 1 over an. And your an is the stuff in here, right? The whole thing in here. So that is lim n to infinity, absolute value of, let's calculate an plus 1. That means negative 1 to the n plus 1, just swapping n for n plus 1. X to the 2 times parentheses n plus 1 divided by parentheses 2 parentheses n plus 1 close paren plus 1 close paren factorial. That is an plus 1. And then rather than dividing by an, I'm going to flip and multiply by an. So that gives me 2n plus 1 factorial divided by negative 1 to the n, x to the 2n plus. There it is. Might look a little scary, but don't worry, it's not. We just need to simplify this power and this expression, and then put the similar pieces together. Let's do that. I'll put the x's in the first chunk. Still absolute values, be careful with those. So x upstairs here, this is x to the 2n plus 2 plus 1 is 2n plus 3. And then this x is x to the 2n plus 1 times. Let's do the negative ones next. Negative 1 to the n plus 1 over negative 1 to the n times. And then the factorials. 2n plus 1 factorial divided by, this is again 2n plus 2 plus 1, 2n plus 3 factorial. In this next step, I'm going to simplify the first two pieces, and I'm going to split up the absolute values. X to the 2n plus 3 divided by x to the 2n plus 1 is x squared. Give him his own absolute value. Negative 1 to the n plus 1 divided by negative 1 to the n is just negative 1. Give him his own absolute value. And then 2n plus 1 factorial over 2n plus 3 factorial. Not much we can do with that straight up algebra-wise in this form. I can observe that those are both positive quantities. 2n plus 1 and 2n plus 3 factorial are both definitely positive. And I'm going to write out the factorials. So 2n plus 1 factorial is 2n plus 1 times 2n times 2n minus 1, all the way down to 3 times 2 times 1. Two n plus 3 factorial is 2n plus 3 times 2n plus 2 times 2n plus 1 times 2n, all the way down to 3 times 2 times 1. So the majority of the work here, as in all these problems, is dealing with the factorials in the ratio test. The trick there, as always, is to write out the factorials, just remembering what they are. Dog shit factorial is the product of dog shit times dog shit minus 1 times dog shit minus 2, all the way down to 1. I see a 2n plus 1 here and a 2n plus 1 here, a 2n here and a 2n here. In fact, I know that this is the product of all positive integers less than or equal to 2n plus 1, which is precisely what 2n plus 1 factorial is. So this whole chunk cancels with that whole chunk. Absolute value of x squared doesn't have any n's on it. I can pop that out, and I can also pop the square out of the absolute values. Absolute value of negative 1 is just 1. So this piece is gone. Multiplying by 1 doesn't do shit. So what's left here is the absolute value of x squared times the limit as n goes to infinity. All this stuff canceled, so my numerator is now 1. And downstairs I have 2n plus 3 times 2n plus 2. What is this limit? Very good. This limit is 0. 2n plus 3 goes to infinity. 2n plus 2 also goes to infinity. So this is 1 over infinity times infinity. So this is the absolute value of x squared times 1 over infinity, which is 0. So L from the ratio test is the absolute value of x squared times 0 is equal to 0, which is less than 1 for all real numbers x. Therefore, the series converges. Absolutely. For all x in the interval -infinity to infinity. So that's your IOC. And the ROC, radius of convergence, is infinity. And this is what we thought was the case, right? This is what I claimed previously, but I just wanted to go through this exercise with you because calculating ratio test limits like these is definitely something that will be on your test. It's something I really want you to practice. A number of your homework problems, of course, from last week involve calculating intervals and radii of convergence. You need to continue that. If there's anything you're stuck on or struggling with there, just let me know. Yes, so the factorial. So remember the factorial of anything. Let me. The trick there is just to remember the definition of the factorial. In general, n factorial, this is the product, meaning multiply, product of all positive integers that are less than or equal to n. And generally we write that as n times n minus 1 times n minus 2 all the way down to 3 times 2 times 1. Right, so we're going to take every integer that is less than or equal to the thing being factorial and multiply it. So right, 3 factorial is 3 times 2 times 1, 4 factorial is 4 times 3 times 2 times 1, 5 factorial is 5 times 4 times 3 times 2 times 1, and so on. So 2n plus 1 factorial, this should be the product of all positive integers which are less than or equal to 2n plus 1. So we're going to start at the top and multiply our way down. The first positive integer less than or equal to 2n plus 1 is 2n plus 1. The next one is the first number beneath that. So just like this, like subtract 1. Well, if you subtract 1 from 2n plus 1, you get 2n. And then you subtract 1 from that. So that would be 2n minus 1. And we go all the way down until we get to 1. So the last few terms are 3 times 2 times 1. Kind of in that same vein, 2n plus 3 factorial would be 2n plus 3 times the number right underneath that, which is 2n plus 2, times the number right underneath that, which is 2n plus 1, times the number right underneath that, which is 2n, times the number right underneath that, which is 2n minus 1. It's up to you how many of these you want to write before you write the dot, dot, dots. But you're going to continue this until you get down to 3 times 2 times 1. So you see, if I divide this by this, these two terms will be left, but this whole string here cancels. Kind of think of it like dividing 3 factorial by 5 factorial. The 3 times 2 times 1 would cancel with the 3 times 2 times 1 and the 3 factorial, and all that would live is 5 times 4 factorial. What's that? 5 times 4. Okay, I know we're right at the end of class time. There's one more thing I need to share with you today. This will go quick, I promise. It's going to sound like it's not, but it will. I'm going to find the Maclaurin series. For f of x equals cos x. Right, same problem as this. Focus, you focus. Same problem as the one we just did, but for cosine instead. Now, one option is to do this shit again. But I said we're going to do this quickly. So can anybody think of a faster way to get a power series, power series for cosine, besides going through that whole table and writing everything out, blah, blah, blah. Well, recall, I just found a series for sine. So if I want a series for cosine and I don't want to go back through all that bullshit, I could just differentiate this. The derivative of sine is cosine. So the derivative of this power series is the power series for cosine. Cos x, which we know is d dx of sine x, is d dx of the power series for sine x. And when you differentiate a power series, you get another power series. So that's how we're going to do this. Yeah, and it does work out to be basically what you get by swapping all the 2n plus 1s to 2n's. But we got to justify it. We got to explain why that's the case. So if I'm going to come in here and take the derivative of this thing, remember the derivative doesn't see any of the n stuff. It just sees x's. The derivative is a d dx derivative. So I don't differentiate the -1 to the n. I don't differentiate the 2n plus 1 factorial. I just differentiate the x. I'm going to leave the starting index off for a second because we need to talk about that. I leave the -1 to the n over 2n plus 1 factorial, and I just differentiate this. The derivative of x to the 2n plus 1 is 2n plus 1 times x to the 2n plus 1 minus 1, which is just x to the 2n. This is correct, but it can be simplified, and also we need to say what the starting index is. Why did I leave the starting index off? Why haven't I said n equals 0 down here yet? Well, let's see, it might. So recall that we bumped the starting index up by 1. What's the rule? If and only if the original series when do we bump the starting index? Very good, if the starting term is constant. So we bump this up to a 1 if and only if the starting term for this series is constant, if and only if the original series begins with a constant term. So my question for you is, does this series begin with a constant term? The sine series, the one that we're differentiating. Well, if I start writing out the terms of the series, I get, when n is 0, I have negative 1 to the 0 over 1 factorial times x to the 1. That's x. When n is equal to 1, I get negative 1 over 3 factorial times x cubed. When n is equal to 2, I get positive 1 over 5 factorial x to the 5, and so on. So does this series begin with a constant term? No. The starting term here is an x. So I do not bump up this starting index. Stays n equals 0. The other thing we can do here is simplify the 2n plus 1 factorial with the 2n plus 1 here. I will leave that as an exercise to you, as we are out of time. 2n plus 1 factorial is 2n plus 1 times 2n minus 1 times blah, 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 down to 1. When you cancel the 2n plus 1 up here with the very first term of the factorial here, what's left is 2n factorial. I can show you the work briefly, I guess. So negative 1 to the n times 2n plus 1 over 2n plus 1 factorial. That's negative 1 to the n times 2n plus 1 divided by 2n plus 1 times 2n times 2n minus 1 all the way down to 3 times 2 times 1. And you can cancel just the first part here. And that is negative 1 to the n over 2n factor. So that's the whole series. I know we've gone over a little bit. Feel free to leave if you'd like to. Maybe take a screenshot so you've got this to digest if you need it. Practice working with Taylor's theorem. Right? It's necessary. As with everything in this class, practice is necessary. And I promise with practice, you will get more comfortable with it. The following series you need to memorize forever and ever on. I'm here in the textbook to section 1110. Here they are. So it's page 768 in your book. You've got the geometric series, e to the x, sine x, cos x, inverse tangent, natural log of 1 plus x. This bottom one, you don't need to worry about. I will show you some special cases of this, but I'm not going to require you to remember the Newton binomial theorem. It's a little bit wonky. So you have to remember all of these except for the last one, right? You gotta know these guys. You gotta know them dead cold by heart, the same way you know that the derivative of sine is cosine. It needs to be like automatic. On Wednesday of this week, we're going to practice working with these things, these series, seeing what sort of problems we can solve now that we couldn't solve before. There's lots of them. And we're also going to talk a little bit about those TN, the Taylor polynomials, because those turn out to be basically the more practical form of these infinite series. These infinite series, they go on forever, so they're kind of hard to work with. But the Taylor polynomial, which is a partial sum of these series, is much easier to work with. So that's next time. Next time we will see what sort of problems we can now solve, having these fancy new guys here. We will look at one special case of this, and then we will look at some Taylor polynomials. And that will be the end of our study of power series. You'll be glad to hear after that, no mas. So work hard on this stuff, get yourself to a place where you're reasonably comfortable with it. And that is it. I'll see you guys next time.